In this lesson, we're going to understand how ultrasounds are produced, how they're used for medical diagnosis. So first, we need to understand how ultrasounds are produced. You will see one word in your syllabus, that is transducer. Transducer basically means that this is a device which converts one signal to another signal, or primarily one signal or one type of energy into electrical. So it could be sound to electrical. So mic is a transducer, right? It could be converting, let's say, mechanical energy into electrical energy, right? The crystal, piezoelectric crystal that we're going to talk about. So what is a piezoelectric crystal, by the way? It's a silicon oxide crystal. Sometimes it's made out of different elements, but that's not a part of our course. What happens is that when you apply pressure on this, the crystal structure changes, which causes a certain voltage to appear on its relative poles. Now, again, this detail is for the understanding of ultrasound. This is not primarily required in the answer. You can just simply write down a statement that applying pressure causes an EMF to appear on the structure of the crystal. So when you apply pressure on it and try to squeeze this, it looks something like this. And when you try to pull it apart, it looks something like this, which eventually causes these negative and positive regions to appear. Sometimes it will be positive, sometimes the same region becomes negative because of the change in shape, which is done because of the change in pressure. Now we can do this mechanically, right? But of course, this is not why we are using the crystal. What we are going to do is that we're going to use it in the opposite way. We will apply electric current on our own, right? We will supply electric current, and because of this, the shape of the crystal will change. Now, we are applying or going to apply an AC signal to the crystal. Why do we want to do that? Because sometimes the shape of the crystal is going to be like this, sometimes it's going to be like this. And because of the change in the shape of the crystal, the face, which is close to the surface, which is close to the material or medium, it's going to produce a sound wave because of the change in shape. And since we're dealing with ultrasound, we know that sound is a series of compression and refractions. So when the crystal actually moves out, it compresses the air particles that are close to them. When the crystal squeezes in, for example, that causes these particles to move or spread apart. So we can control the frequency of the AC signal that we're providing to the crystal. Basically, that is going to control the frequency of the sound wave that is going to be produced. Okay. Now, we understand that how piezoelectric crystal can be used to create an ultrasound or to create an ultrasound. This is also going to be used to, you can say, detect ultrasound as well. Now, we do the same process in reverse. You see, how ultrasound basically works is that, for example, if this is our boundary or this is the organ that we want to detect, we first use the same transducer to produce ultrasound, and then we wait for that signal to come back. It is happening very quickly, so you don't realize this happening if you look at an ultrasound machine, but this is what's actually happening. So when the sound wave actually reflects back, the same transducer experiences a change of shape and wobbles between these two positions, right? And when it does so, it is going to detect, or it is going to change shape, and as it changes shape, it produces an electrical signal. That electrical signal is then fed to the computer and creates the image. So first, we provide electrical signal to change its shape, then we wait for that signal to come back so that it can change the shape of the crystal again to produce electricity that we gave in the first place. That is how the ultrasound basically is going to work, right? So we understand the first two parts of the syllabus. Basically, this is what the summary is going to be. And then we understand on point number 3, how this information can give the information about the structure. You can read about this in the book as well, but I haven't found any questions that actually want to dive into point number 3. But point number 4 is where this mathematical aspect starts from. Now let's try to understand these equations. You can take a screenshot of this image. What the examiner is going to do is going to ask you about these two things: how ultrasounds are generated and how they are detected. This question goes from 3 to 4 marks. This question also goes from 3 to 4 marks. And combined, this question goes for approximately 6 marks. You can see this in this question from October-November 2013, paper 4-2, question number 10, part A. He says, lay down the principles to uses of ultrasound to obtain diagnostic information. So what you're supposed to do in this question, first, you're going to talk about generation, how ultrasounds are being generated, and then you're going to talk about its detection. right? I've laid down this question because I primarily ask my students to memorize the marking scheme because we understand how the ultrasound works now, right? So a good idea would be to memorize the marking scheme because one question from medical physics is a must, is going to come in P4. This is the marking scheme of the question, right? And you can see, pause the video and read about the points. This is exactly what I've discussed in these points: how ultrasound works, how the crystal functions, and what's the job of the crystal. Anyways, not wasting any time over here because as I've asked you earlier, we understand how ultrasound works. We just have to memorize the points now, okay? Now let's move on to the acoustic impedance. That was point number, I think, 4. Yeah. So acoustic impedance, simply defined as the product of density of that medium where the ultrasound wants to move through. It could be a tissue, it could be fat, it could be skin, it could be any organ inside the body, multiplied by the speed of sound in that medium. Could be fat, could be muscle, could be bone, could be anything, right? Now, the unit of this system is going to become very simple. This is density is kg per meter cube and speed is meters per second, right? So when you simplify this, what does that become? This becomes kg m minus 2 s minus 1. Simple as that. What is the meaning of this? What is it trying to do? Basically, this acoustic impedance is an indicator of the material that the ultrasound is passing through. Of course, fat, muscle, bone, lungs, your kidneys, your stomach are going to have different densities. The speed may vary slightly, but the densities will be very different. Based on this idea, the value of acoustic impedance will be different for all the organs. So primarily, from an engineering standpoint, acoustic impedance just helps us differentiate between different organs and tells us what we are looking at. Okay, that's all that the importance of this variable or this value is. Nothing more than this. Now we move towards reflection coefficient. What is reflection? What is transmission? Now, when we introduce this ultrasound beyond a boundary, let's say this is our organ that we want to test, that we want to read about. We introduce sound wave from the outside. This is air. Let's say this is your skin. This could be fat, for example, and then you find the organ, right? What happens to the sound wave? When it encounters a boundary, boundary could be any difference of medium between two organs. Even this is boundary because it's a boundary between air and fat. Now, this will also be a boundary because it's a starting point from fat to the organ, right? Now, anywhere where we will find different materials, different organs, we will call that point as a boundary. So over here, we define this as a boundary. This could be medium 1, this could be medium 2. We don't know. This could be fat, this could be a muscle. We don't know, right? But how do we differentiate them? As I explained earlier, acoustic impedance is the value that tells you what's what, okay? Are you dealing with fat? Are you dealing with muscle? It doesn't matter. Now, when we get to this reflection, how we deal with variables, how we deal with mathematics, what is it trying to tell you? Now, there is a ratio that is known as reflection coefficient or reflection ratio that is actually called as alpha or represented as alpha. This is IR means reflected wave and I naught means the incident wave that you introduced. And of course, the incident wave has a higher power. It has a higher energy because this is what you introduced into the system, right? Then we encounter two more waves. Be very careful what I'm going to refer to. This is the reflected wave. At every boundary, sound wave or ultrasound is going to get reflected. It is upon us. It is our choice whether this reflected wave has to be high or whether we want to keep it low, based on this idea that we want to make sure that everything gets transmitted in the tissue. If I want the sound wave to make sure, or if I want the sound wave to travel into the tissue, I will make sure that the variables of the formula that I'm just going to write down should be in a certain configuration, and we'll get to the discussion later. So what is this formula representing? Be careful, right? The incident wave is the I naught, right? And the reflected wave is the IR that I'm dealing with over here. Now, a bit of an odd formula because we are basically interested in the transmitted wave. I don't want the wave to get reflected back. I want it to be transmitted in so that I can reflect back from the organ I want to find out. I'm interested in, right? But of course, reflection is also important. Why is it important? Because what if this was the organ that I was looking for, right? I want the sound wave to reflect back and come to me so that I can detect it and represent it on the screen. So reflection is also important. Transmission is also important. So in my lecture, I will label this transmitted wave as IT, reflected wave as IR, and incident wave as I naught. Okay, this formula is with the reflected wave. Transmitted wave is not discussed in the formula, but I will tell you how you can involve this in this equation. So the formula goes something like this: Z1 minus Z2 whole square divided by Z1 plus Z2 whole square. What is Z? Z is the acoustic impedance. And where do I find them? This is where they are written. And of course, the data is given to you in the question that you are dealing with such and such medium, dealing with fat, muscle, XYZ, whatever there is, right? Okay. Now, notice that this is with reflection, and this is labeled as A, and it will always come out as a certain percentage. For example, it could come out as 0.59. It could come out as 0.8. But if you convert this into percentage, this will be 80%. This will be 59%, right? This reflection coefficient means that if the, let's say for the sake of discussion, I choose the value to 80%, okay? This means that if 100% incident wave had the power, right? The power of the incident waves were considered to be 100%. 80% reflection means that 80% is going to come back to you. It's reflected from the boundary, and only 20% was sent into the organ or into the skin or into the system which you were trying to figure out. Okay, so how to get this number? If you want to find out the transmitted wave, if you want to find the intensity of the transmitted wave, then simply 1 minus alpha would suffice, because alpha is a percentage, right? It's 0.8. Full strength is 100%. So if I take the subtraction, this will tell me the information about the transmitted wave. Okay, so reflection coefficient is alpha. This is for reflection, and transmitted is 1 minus alpha. Simple, right? Okay, no need to change this formula. Just find out the reflected and subtract this from 1 in terms of percentage, and you will get the transmitted wave. Okay, all right. Now, one discussion that he generally does is about the reflection coefficient in terms of acoustic impedances between two mediums. Should they be same? Should they be different? What happens if they are different? You see, if the values in the formula, it's a mathematics problem, not a physics problem, right? Try to understand. So alpha is a reflection with incident equals to Z1 minus Z2 whole square divided by Z1 plus Z2 whole square. Please notice that if there is a large difference between them, for example, if Z1 is 1000 and Z2 is just 1, the difference of this answer will come out as 999. And the value in the denominator is going to be 1001 because they're being added together. Now, in terms of mathematics, since you're taking square of both of them, this answer is going to come out nearly equal to 1. How? It maybe come out as 0.99 or something like this, which is almost equal to 1. What does that mean? If this answer comes out as 1, that means that IR divided by I naught is equal to 1. If I take I naught over there, this becomes IR equals to I naught. What does this mean? It means that whatever incident wave you introduced, it was 100%. All of it, 100% of it has been reflected back. Nothing got penetrated into the medium. Now, in some cases, this is what we want. But in most of the cases, this is not what we want. What we want is the wave to penetrate into the body and ultimately reach the organ that we're trying to search for, right? So now this is what happens when the difference is very large. Everything gets reflected back. Now, what if the difference was very small? For example, this is 1000 and this comes out as 990 or 999. This answer would come down to, let's say, 10, right? The difference will become 10 squared divided by, and this will become 1990 square. Now this answer is going to get very, very small, almost equal to 0.0 something, right? What does that mean? It means that IR divided by I naught has become 0.00 something. If you take I naught over there, you realize that IR is now equal to 0.0 something, let's say 0.03 times I naught, which means that only 3% of it was reflected back, and the 97% has been transmitted in. So in this circumstance, it would go something like this. 100% was introduced, 3% got reflected back, and 97% got in. This is what we want generally, so that nothing gets reflected back. Most of it goes through the body and penetrates through the body, okay? All right, also look at this question. It's a good question in terms of covering the full ultrasound question, right? Now we move towards attenuation equation, okay? Now attenuation equation, you will find this in the syllabus over here. Point number 4 is covered. Point number 5 is point number 5 is also covered, right? We've done acoustic impedance, we've done reflection coefficient. Now we're moving towards attenuation constant or attenuation equation. Basically, attenuation means loss of energy or power, okay? So loss of power and energy, how and why? You see, when, for example, this is our organ, and this is air, this is your skin, and let's say this is some fat, or this is some muscle. If you introduce ultrasound from the outside, some of it gets reflected back as IR, some of the percentage is already lost. The wave that is transmitted into the fat or into the skin, as it moves through skin, it has to encounter matter, it encounters skin, it encounters other types of tissues as well, and it loses power. Let's say if this was 60% at the point of entry, at this point, it is quite possible it has come down to 27%. Why? Because as it moves through matter, it loses energy. It gets attenuated. So to compensate for this effect, we have another equation, which is I equals to I naught e raised to power minus mu x. Now, what is mu? Mu is the attenuation. It's called attenuation coefficient. It will be given to you. And x is the thickness through which this radiation or this X-ray was moving, right? I will show you how to use this equation. Now, please be advised, when you encounter a boundary, you want to figure out what goes in, what goes out, you have to use the attenuation. You have to use the acoustic impedance formula, the reflection coefficient, which was Z1 minus Z2 divided by Z1 plus Z2 whole square, like this. But when you are moving through matter, you have to use this equation, right? So we are going to use both equations to fully solve questions and try to learn how to do this properly. Let's try to understand the attenuation equation a bit better, and then we're going to move on to the next question. Okay, so aluminum block placed, okay, fine, we understand this. A cross-section of the model of the finger is shown, okay, fine. Now, notice that the attenuation constant of the bone is different from the flesh, right? Bone absorbs more and tissues absorb less. Although the question is from the X-ray part of this syllabus, but we want to understand how to use this equation. So ignore if you don't understand the X-ray machine or something like this, but we want to use this equation. We want to learn how to use this equation. So please be advised. Okay, so first he says, calculate the ratio of incident beam, which is generally represented as I naught, what we have introduced, and this is represented as I, what we got back in this formula. I equals to I naught e raised to power minus mu x. Okay, all right. So he says the divided by the intensity of the emergence. So this is what he's looking for. Generally, we try to solve this for I over I naught, but in this question, he has tricked you to solve I naught over I. No problem. We can put this in the equation as well. So this is going to be I equals to I naught e raised to power minus mu x. But first, let's figure out what's mu. Now, first we have to go through A to B. He's asking us for A to B. The thickness of the tissue is already given to you as 2.4 centimeters, okay? And the reflection attenuation coefficient is 0.27. I'd also notice that this is per centimeter. This is also centimeter, so no need to do any conversion. So this is going to look something like this. I equals to I naught e raised to power minus 2.4, I think. Yes, this is 2.4 and 0.27. So 0.27 multiplied by 2.4. Please be advised, no need to convert because both are in centimeters. Now notice the question was regarding I naught divided by I. If I do that, if I take I over there, then I have to take E over there, which makes this power become positive because E raised to power negative, or you can say E raised to power minus x is as equal to 1 over E raised to power x, right? So if I take this over there, this is going to become positive power. So this will be 0.27 into 2.4. When you calculate this, this answer is going to come out as 1.8 something 5, but that becomes 1.9. So this is going to be 1.9. Then about beam C to D. Here we learn another thing about dealing with this equation is that if you encounter consecutive mediums, they get multiplied together no matter what. Okay, so let's see what happens. Now notice that this X-ray not only has to encounter some flesh, but it has to go through bone and then flesh again and then exit the medium. Okay, so how much of it is bone? That is 1.1. How much of it is flesh? So that would be 2.4 minus 1.1. Some of it is here and some of the flesh is over here. Do we need to do that separately? You can do that, but it wouldn't serve any purpose because you have to multiply everything together. You see, when you encounter different medium again and again, you just keep on multiplying the factor of e raised to power minus mu x with the consecutive materials, right? Because this is I naught and this is I. Whatever keeps coming will get multiplied. Okay, so what does this look like? This is going to look something like this. I equals to I naught e raised to power minus mu x multiplied by e raised to power minus mu x. The first factor is for the bone. The second is for the flesh, right? Now, again, since we're dealing with I naught divided by I, let's take this over here and this over there. This is going to come in the numerator. So this becomes e raised to power positive mu x multiplied by e raised to power positive mu x equals to I naught divided by I. Now let's replace the values. So this is going to look something like this. I naught divided by I equals to e raised to power 0.27 into 1.3. How did we get 1.3? That was 2.4 minus 1.1 to find out the flesh in these two sections. Multiplied by e raised to power 3 into 1.1. Why 3 into 1.1? Because 3 is a coefficient for bone and the bone is 1.1 centimeters thick. Now, when you're done with this, you find out that the answer is 38.5. This is 38.5. Okay, so I hope we understand this attenuation equation, how to use it and how to put in values. Okay, moving on to this question. This is a very interesting question. It opens up or clarifies almost all of the concepts of ultrasound, and it actually tries, you can say it's a bit difficult, but no need to worry. We're going to understand how to solve it. All right. Now, again, this is an ultrasound beam. This would have been I naught, but since some of it has been transmitted in, this is the starting point. So we're going to consider I1 as our I naught or the starting point. He mentions everything. What is I1, what's I2, what's I4 and I3. He talks about everything. You can pause the video and read about it on your own. First question he tells you, he asks that time interval between the short pulse ultrasound initially entering the layer of the fat and then coming back. He says there is an ultrasound entering the fat, it bounces back and then comes over here. So the time interval to go and then come back, this is the time interval he's asking you. Okay, so no need to worry about it, no issues. What first, we need to find the speed of sound in this medium. So we know that based on this marks of the question, there will be multiple steps involved. So first I use z equals to density multiplied by the speed of sound in that medium. The speed is not given, which is what I want to find out, but the density is given, the acoustic impedance is given. So this is going to be 1.4 into 10 to the power 6 equals to 940 multiplied by c. C comes out as 1489 meters per second. I'm rounding it off to 1490 meters per second, right? It wouldn't make any difference. Next, I want to use the formula for speed equal to distance over time. Speed equals to distance over time. Now, since we are dealing with twice the distance, let's consider this to be the distance d. Since one time it has to go, one time it has to come back, so this distance has to be taken twice. So this will be changed to a factor of 2 times d, right? I find the speed, which is 1490, equals to 2 times into 1.1 into 10 raised to the power minus 2. Why 10 raised to the power minus 2? Because this is in centimeters. I have to convert it into meters. Divided by time t. When you find time t, this comes out as 1.47 into 10 raised to the power minus 5. So this is going to be rounded off to 1.5, 10 raised to the power minus 5 as 2 significant figures. Now, this is also an easy part. The next part is a bit difficult or tricky, you can say. Now, how to solve this part? He's asking you to find out the ratio of I2 to I1. Notice that is there any boundary over here? Is there a change of boundary? No, it is moving through a single tissue. Now, when it's moving through a single tissue, I will have to use the equation of attenuation, which is loss of power moving through mass. So, but what's I and what's I naught in this situation? I0 is generally what was introduced. So I1 was introduced. So this is going to be called I1. I is what is being received. So I2 is being received at this end. So I will take that as I2. This is going to be e raised to the minus mu x. Okay. Now, since I2 or I1 was asked from me, I will arrange this equation, take this I1 over there. This is going to look like I2 divided by I1 equals to e raised to the minus mu x. Now let's go back to the table. Let's see if we can find out the values. Mu is 48. And the distance, or you can say the thickness of the tissue for which the sound had to travel is 1.1. So very simply put, e raised to the minus 1.1 into 10 raised to the minus 2, right, into 48. Now notice that 48 is actually given as per meter. Let me erase this and show you. This is given as per meter. So I have to convert this centimeter into meters. Previously, we didn't do that. Okay, that's why this into 10 raised to the minus 2 factor is involved. Okay, so when you're done solving this, you realize that this comes out as 0.589, which will be rounded off to 0.59. I2 divided by I1. Please notice, what does that mean? Let's write down in simple terms. So if this is considered as 100%, when it comes to this point, it has already lost 59%, or you can say approximately, let's round it up to 60%. Okay, so at this point only 60% reached and 40% was lost. Okay, so this is what this means. Okay, this was what this number means. So this is actually 0.59. In comparison to this, what was this? Okay, so 60% is received, 40% was lost while traveling through this tissue. Okay, anyways, now this question is a bit tricky. Okay, and of course I've included this question in this lesson so that you can understand another technique to solve these questions. Although I've seen this question very rarely, but I've included this because it's different from the rest of them. Okay, so intensity, he says I4 in terms of I1 is 33%. Now please don't ignore this percentage sign. This means that I4 divided by I1 is 0.33%, which means 0.0033. Okay, percentage is actually divided by 100. So please note this. Okay, he wants you to find out I3 by I2. How we are supposed to do that? You see, we can develop a relationship over here. How can we do that between I4 and I1? You see, if you start at this point, then first you encounter the ratio I2 divided by I1, okay, for any mass traveling through this. Then you encounter this reflection coefficient at this boundary, which was supposed to be calculated as Z1 minus Z2 divided by Z1 plus Z2 whole square. This is what we use to calculate this, that how much is going to go in and how much is going to come back, right? But we don't have those acoustic impedances over here, so we can't do that. This is why he is asking you this, because we don't have the acoustic impedances. Anyways, we can find it. If we were to do this, okay, so how it would have been done? That would have been I3 divided by I2, okay, right? How? Because I3 would have been the reflected wave and I2 would have been the introduced wave. And this is what the equation is about. Alpha was equal to the reflected wave divided by the introduced wave. This was equal to Z1 minus Z2 divided by Z1 plus Z2 whole square, right? So in place of R, I'm putting 3, in place of putting 2, right? Okay. Moving on from this point, multiplied by, again, this wave has to come back, loses some power, loses some energy. So over here, this would have been I4 divided by I3. Okay. This would have been equal to, notice that I3 gets cancelled with I3. I2 gets cancelled with I2. We are left with I4 divided by I1. So this is I4 divided by I1. It's more like the chain rule you do in mathematics. I think integration probably. I don't remember that, but if you've done A2 mathematics P3, I think you're familiar with integration. This is where you find it. So this is actually in turn, you can say, inspired by that method. Okay, so let's put in the values. Now notice I'm going to erase this. Okay, all right. So what's what? So at this point, we can see that going from this point to this point was actually going to cost us 0.59 because we calculated this in the previous part. Coming back from I3 to I4 would again cost us 0.59. So this variable is 0.59. This variable is 0.59. This is what we want to find out, and this was already given in the question as 0.033, right? So let's write this down over here. Simply put, this is actually I4 by I1 equals to I2 by I1 multiplied by I3 by I2 multiplied by I4 by I3. This is 0.0033. This is 0.59. This is what we want to find out. This is also 0.59. Okay. And when you substitute everything and you eventually find out I3 by I2, you get the answer as 9.48 into 10 to the power minus 3, which will be 9.5 power minus 3.